Welcome to super cool video number 1. We're going to introduce the trace-determinant plane. I'm going to abbreviate trace-determinant, TD, because that is too many letters to write. So I'm sure you have the burning question, what is the trace of a matrix? Well, or unless you already know the answer. But let's put some framework, let's take a step back and let's introduce the problem that we're working with. And it's the same problem we've been working with for this entire chapter. Specifically, let's say the matrix A is A, B, C, D. dy dt is A times Y. It's the same system that we've been doing this whole time. Then we know the determinant of the matrix, right? You know the determinant of this matrix. You've been calculating determinants of matrices the whole chapter. The determinant of the matrix is A times D minus B times C. No problem. Well, the trace of a matrix is written TR of A, and all it is adding up the diagonals. That's it. That's all the trace is of a matrix. So this is called the trace of a matrix. Let's call the determinant D and the trace T. Okay? Now, why do we care about the trace of a matrix? Well, there's many answers to that, all of which you can get answered in a linear algebra course. Why do you and I care about the trace determinant? Why do you and I care about the trace of a matrix? Well, I'll answer that indirectly. What do we know about eigenvalues? We can find eigenvalues. They're the roots of the characteristic polynomial. So our eigenvalues come from the characteristic polynomial, which is just going to be A minus lambda I. So A minus lambda, D minus lambda. Let's see, minus B times C. We want that at equals 0. That's not how you write that, Jason. We want that to equal 0. Let's simplify a little bit. I'm just, humor me. I just love doing math. When we FOIL all this out, all right, what are we going to get? We're going to AD. Let's see, we're going to get a minus A lambda minus D lambda. Let's just write it as minus A plus D lambda maybe, right? That's the same thing, minus A lambda minus D lambda. Oh, I'm not done. Let's keep going. Last part of foiling is lambda squared. Well, now if I were to just kind of rewrite this little characteristic polynomial a little bit, what are we gonna get? We're gonna get lambda squared minus A plus D times lambda plus AD minus BC. Well, do you notice anything? Do you maybe notice that this is the trace of our matrix and that this is the determinant of our matrix? So our characteristic polynomial is just lambda squared minus the trace times lambda plus the determinant of our matrix. Now, this is not the cool part. You might think this is really cool. You might be getting excited, but this is not even the part worth getting excited about. It only gets better from here. So we want to know the roots of this polynomial. And of course, they're going to depend on the trace and the determinant of the matrix. So we just take this equation and we say, all right, well, I know how to solve this. I've been doing the quadratic formula for years, probably. The solutions are going to be negative b, which in this case is positive t, plus or minus the square root of negative t squared, which is the same thing as positive t squared, minus 4 times a, which is 1, times d, all over 2 times a. Now, remember what we said. We said depending on our eigenvalues, that really tells us what qualitative behavior we have for our system. It gives us information about the equilibrium. It gives us a lot of things. So of course, our eigenvalue, if it depends on t and d, the trace and the determinant, then we could kind of graph some relationships, right? Because all of these depend on the trace and the determinant. So we're actually going to graph those on this trace-determinant plane. I'm getting ahead of myself a little bit. Remember, looking at this equation, that we have very different types of behavior depending on this discriminant. Right? Specifically, we know that if the inside of this is positive, then we have distinct real roots, which means distinct real eigenvalues. Oh, that's going to be good information about qualitative behavior. And of course, if it's negative, then we have complex eigenvalues. We'll have a spiral sink or a spiral source. And if it's 0, something very interesting happens as well. We get repeated real roots. Now, when does this equal 0? Well, if our horizontal axis is the trace of our matrix and our vertical axis is the determinant of our matrix, I can graph this, right? Let's add it to both sides. So when 4d is equal to t squared, that's when d is a quarter t squared. That's easy. That's just a little squat parabola. It's just a parabola that looks like this. This is when t squared minus 4d is equal to 0. And this is what's known as the repeated root parabola. Why do you think it's called that? Well, of course, because on this parabola, you have repeated roots. If the square of the trace minus 4 times the determinant equals 0, then you're not plus or minusing anything. Your eigenvalue is just t over 2. Your eigenvalue will just be t over 2. So everywhere on this parabola has a repeated root. Every system that has this relationship between the trace and the determinant will have repeated roots. And furthermore, we can say more things by incorporating this, right? If this is positive, something happens. Now be very careful, right? If this is positive, that's when t squared is bigger than 4d. That's when d is less than a quarter t squared. So this being positive actually is beneath the parabola. So everywhere here, we're going to have real roots. Okay? And then similarly, everything in the other region, this is all going to be complex. So what we're going to do in the next video, and we're not done with this video yet, but what we're going to do in the next video is actually break this down even further. Okay, we have complex if the relationship between t and d is up here. We're going to have real if it's down here. But is there going to be a difference between if we're on the right side or the left side? What happens if the determinant is 0? Does that do anything specific? How can we classify whether something's a source or a sink? How do we see how, like, remember we said that those repeated roots are kind of borderline cases. Are there other borderline cases? How can we visualize all the different possibilities? And we can put them all on this graph with some really cool mathematical analysis that we do in the next video. But for now, we'll just pause and appreciate and say, oh, okay, I can see 3 big cases, right? This was 3.2. This was 3.4. And when we were on this parabola, that was 3.5. Just kind of cool. And then we'll subdivide even more. And it's really cool. Let's do an example. Let's use the trace-determinant plane. Okay. Use the trace-determinant plane to analyze the roots, or let's just say analyze the eigenvalues for a matrix that looks like 1, 2, 3, 4, and for a matrix that looks like 2, negative 300, 1, comma 2. All right, let's call this part A. Let's call this part B. Do it color coded. Well, for part A, it's very similar, or it's very simple. What is the trace? Well, you might not remember. That's okay. The trace is just adding up the diagonals. And that'll be the same for 3x3 matrices, 4x4 matrices. The determinant for 3x3 matrices is not quite as nice. Google what the determinant of a 3x3 matrix is. But it's fine. You can do it. It's just not as nice. And the determinant is going to be 4 minus 6. Okay, well, if the trace is 5 and the determinant is negative 2, well, we must be somewhere over here. We know we have distinct real roots. We know our lambda are distinct and real. So we're not quite sure whether it's a source or a sink yet, but we know it's going to be a source, a sink, or a saddle. In the next video, we'll talk about which one exactly it is. Spoiler alert, it's a saddle. You could also find that by finding your eigenvalues. But we're just getting practice using the trace-determinant plane. Letter B. Let's not even find B, actually. Why did I throw this negative 300? And I'll tell you why. I put this negative 300 in because I wanted a specific kind of eigenvalue. And because I know what the trace-determinant plane looks like and what the repeated root parabola is, I can force myself to be in one of these behaviors by making one of these values really big. Notice that my trace is not very big. But what I did is I made my determinant huge. I did that because I wanted a complex eigenvalue. And I knew from this picture that if I kept my trace not too big and made my determinant really, really big, I'd be guaranteed to be up here. And we'd have complex eigenvalues. So that's why I made that example. And of course, you can see the trace is indeed 4, and the determinant is 4 plus 300. So yeah, we're at 4, 300. We're off the charts. But certainly, lambda is complex. We'll be able to say more things because we know the trace is not 0. So we know we're not a center. Because the only way you can get a center is if there's no real part. And we notice that the real part is always the trace divided by 2. But that's the next video. Okay. But isn't this cool? Isn't this cool? The next video is going to be super fun, a little bit complicated mathematical analysis, but it should be very educational. And the results are not hard to use. So we'll give you like a cool proof for where it comes from. And I want you to just enjoy that. And then the result is easy to use. But until next time, I'll wait. I don't have to wait that long. I'm going to record it right after this one. You can wait as long as you want. Bye-bye.